All right, chemistry. We have just finished learning about nuclear equations. Remember, you have to think of these as equal signs. This would be a zero. You have to find silicon on the periodic table, which is 14. And then phosphorus is 15. So this is 0, -1. You're going to look at the nuclear equation, 0, -1 beta particle. Again, this one would have to be a 4, and then polonium. Polonium is 84, and it changes into lead, which is 82. So that's 2. That would be an alpha particle. So those were nuclear equations. Today, we are going to start learning about half-life. So the objectives today: define half-life, determine the half-life of a nuclear decay by looking at a graph, and then solving half-life problems. And use the list of isotopes or radioactive isotopes. So that's the objectives today. So here's the half-life of some radioisotopes. Carbon-14, it takes 5,730 years. Uranium-238, it takes about 4.5 billion years to decrease its half-life. And so the time it takes for half of the radioactive sample to decay, it describes the rate of decay. And if it's less stable, it's a faster decay. Like, for example, Pa on the periodic table is protactinium, and that takes only 0.0016 seconds. So that's very radioactive. Bismuth, pretty radioactive. Uranium, this one's a stable type. So the less stable, the faster the decay. And basically, when you're talking about decay, you're talking about the nucleus breaking down and the neutrons in it. So after each half-life, you get half of the sample. So say you start at 100%, half the half-life is the first half-life, 50%. The second half-life, you take half of 50%, you get 25%. The third half-life, you take that 25%, you half it there. The fourth half-life, 6.25%. Fifth half-life, 3.12. Sixth half-life. So each one, you half it down. So you take the 50, and then you half it, and half it, and half it. It never really goes completely away. But, up here it says 50% then transmutes into a different element, 50 of the 50. Then 50 of the 25 transmutes into another element. This leaves 12.5, and it just keeps going and going. So for example, if you had 1 gram of bismuth 210, it's a beta decay, and that changes into polonium. Okay, so if we were doing the half-life, if you had 0.5 grams, half of that, and it would be day 5. So remember, on that first chart you had, I'm going kind of back, but that first chart, bismuth, it takes 5 days for its half-life. So I will go back, sorry. So then after that, you're going to get 0.25 grams. That's 0.75 grams of polonium-210. That's day 10. Then after the next 5 grams, or 5 days, you're going to have 12 grams of bismuth-12. So again, everything's halving this way. These are going up. And, this is how much of the polonium, the next element, that's increasing by 25%, by 12%. If you have 0.31, the two numbers I really want you guys to concentrate on are like the grams and the time it takes. I don't care about the other element. So, you know, it keeps going, 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 going. If you need to pause this and write down, you know, the days or whatnot. All right, so radioactive decay. Here's your initial radioisotope after its first half-life. Half of that is existing. And then its second half-life, 1/4 of that would remain. After its, wait, 1, 2, third half-life, an eighth remains, fourth half-life, you know, and these are how many days it takes. So on the graph, you know, radiation gets weaker over time, the smaller it gets. And, you know, the graph, the days goes up, the amount goes down by half each time. Each half-life reduces the amount of radioisotopes. An amount never becomes zero. You're always going to have some part of that decay left. After 10 half-life samples, it's considered non-radioactive. So here's the use of radioisotopes. You can use it in radioactive dating. So that if you want to tell how old a fossil is, or, you know, the time it takes. Nuclear medicine, radioisotopes are used in. Miss Flaherty, you can ask her about all her procedures. She's had a lot done with radioisotopes. And food preservation. Most of our food is preserved with radiation. So radioactive dating, it estimates the age of very old objects. It uses a substance called carbon-14. And other possible isotopes, you have uranium-235, potassium-40, and samarium-147. So in our atmosphere, we have nitrogen-14. And in all living things, we have all three carbon isotopes. We have carbon-12, carbon-13, and carbon-14. They're absorbed by living organisms. If they die, basically the bone loses that carbon-14 and it changes back into nitrogen-14. So that's a beta decay. And you can tell how old something is based on how much of that carbon-14 is left. So the half-life is 5,730 years of carbon-14. It's found in all living things. We have a tiny amount compared to carbon-12. But living organisms maintain carbon-14. They keep it in their system. When they die, after dying, carbon-14 would decay. And then you could figure out, so say you found a bone like of a woolly mammoth. Originally, it would have 100% of its carbon-14. After it died, the half-life of carbon-14, if there was 50% of it left, that would mean that the bone was 5,730 years. If you found only 25% of carbon-14, that would mean the animal was 11,480. If you found 12.5%, that would tell you the age. So each of these half-lives go up by the time it, you know, lapsed. So each one you'd add 5,730 to each of these numbers, and that's how you're getting that. And then the decrease of the amount is half of that. Nuclear medicine, X-rays, radio tracers, radiotherapy. They use radioisotopes in medicine. So you guys know what an X-ray is. I'm sure everyone's had one. It's an image inside the body. CAT scans are also a type of nuclear medicine. They look at different angles. Miss Flaherty's famous eyeball picture, that's a CAT scan, and it's injuries related to the head or brain. Radio tracers are tiny amounts of radioisotopes. They pass through the body and they have a very short half-life, so they don't stay in there. But when you X-ray, I know like I had a bone that they didn't know if it was fractured or not. So they put these, they injected my foot with these radioisotopes and they would congregate at the break site, and they found out I did have a break. If they want to trace your digestive enzymes, you know, they'll give you something to drink, or, you know, and it just goes through your body. You take like a scan of it and they could see if everything's running smoothly or if there's something going on in there. Radiotherapy is direct beams at a specific area. You would shoot a radio, if you radiate or if you had cancer, they radiate you sometimes. You do chemotherapy or they have radiation therapy, and that's a direct gamma ray in the area specific with cancer. They would make that fast growing cancer vulnerable, and that's how those work. And then we also use food preservation to radiation for food preservation. Fresh food is susceptible to mold or bacteria. They irradiate the food when packaged, so it's exposed to radiation to kind of kill off any of those molds or bacteria. Food is not radioactive. The radiation passes through, but it will kill anything that would potentially like make it rot quicker. So that's it for Half-Life. We're going to practice Half-Life problems tomorrow. So just be ready to work on that. They're not as hard as they seem. You know, you go up with time and down with the amount. So that's it. And I will talk to you later.